very relevant about anything. Yeah, so I won't be like maybe the algebraic quantum field theory statement may not be that rigorous. Okay, so one of the major goal of quantum gravity is to study the physics near the singularity of a black hole. Okay, and one of the most promising description of quantum gravity so far we have is the ADS CFT, and this duality provides a CFT description of quantum gravity in an asymptotically ADS space. But the main difficulty of this description is that the degrees of freedom that's living in the bulk are encoded in the boundary theory in a very, very non-trivial way. So we need to really figure out how the degrees of freedom that's living in the bulk are encoded in the boundary theory. And the process of expressing the bulk degrees of freedom in terms of the boundary degrees of freedom is called the bulk reconstruction. So the bulk reconstruction is the first step in the study of physics inside a black hole using ADS-CFT. So if you want to use ADS-CFT tools to study the quantum gravity behavior or the behavior of some state in a black hole geometry or within the black hole horizon, we must first understand how to decode the degrees of freedom that's living inside the black hole. And we have some interesting proposals for doing the reconstruction of bulk fields inside black hole horizon. So we have two proposals. One is due to Papadodimas and Raju, and another one is due to Liu and Litesa. So the proposal due to Papadodimas and Raju basically it introduces some additional operators, or in other words, what we need to do is we have to double the degrees of freedom that is there in the CFT, and the way you do is by introducing so-called mirror operators. I won't be going into the details of mirror operators, but just to remember that we need to double the degrees of freedom in a way. And once we have that mirror operators, we can express the fields that is living inside the black hole horizon as a sum of operators in the boundary CFT and its mirror operators with certain weight factors. Okay, so we need to figure out the weight factor, and also we need to identify the mirror operators. Once we are successful in doing this, then we can express the bulk fields that is living inside the black hole horizon in this way. So another more recent proposal is due to Liu and Lutesa. So they also try to reconstruct a bulk field that is inside the black hole interior using an algebraic quantum field theory operation known as half-sided modular translation. And so I will say more about half-sided modular translation in the later part of the talk. But you just need to remember that there is an operation that you can perform in the quantum field theory. And what you do is you reconstruct the bulk operator inside the horizon by first considering the same operator outside the horizon and find the dual operator in the boundary CFT. So you start with an operator that is outside the horizon, and we already know how to construct an operator if the operator is outside the horizon using the usual bulk reconstruction program. So you take that dual operator in the boundary CFT and then perform a complicated transformation. And that transformation which you are supposed to perform is called half-sided modular translation. And this translation, or the half-sided translation, can be combined or constructed as a specific combination of modular operators associated with the full boundary of the space-time and a subregion of the boundary. I will tell more about this in detail later. But anyway, the thing to remember is that you start with an operator that is outside the horizon in the bulk and find its dual operator in the CFT, boundary CFT, then perform a non-trivial transformation, and that transformation is called half-sided modular translation. You do this half-sided translation, then the claim is that the operator that you obtain in the boundary CFT after performing the half-sided modular translation has a dual in the bulk theory, and that dual field is living inside the horizon. So that's the for an appropriate range of this parameters that is associated with the Hofstadter translation. So anyway, the point is that you can start with operators which you can reconstruct and then do a complicated transformation to this operator, and that will give you the dual of operator that is inside the bulk, inside the horizon of the black hole. So these are the two proposals. One proposal introduces additional fields or additional operators. Basically, you do the doubling of the fields, and in the second proposal, what you do is you do a complicated transformation. Okay, so these two, the two proposals are supposed to be useful even for a black hole which have only one side. Even for a one-sided black hole, the claim is that you can use the Papadodimas-Raju proposal and half-sided modular transformation to do the reconstruction of fields that is living inside the horizon. But so we know more about this construction in the case of eternal black hole. Okay, so we know, I think we have a better understanding of this proposal in the case of eternal black hole, where we have two sides. And in this talk, I will be focusing only on eternal black hole. So we can consider an eternal black hole, and this geometry is given here. So I will be considering a two-dimensional black hole, eternal black hole, and it has two sides. It's shown here. So you have the right side of the black hole that is given as the triangle shaded with a light green. That's the right side of the black hole. And in the left side, you have another triangle, and that's shaded with light blue. And the prescription is that you have such an eternal black hole in ADS2, and that is dual to two CFTs. Basically, a CFT that is living in the right boundary of the eternal black hole. And I have denoted the Hilbert space of that CFT as HBR. And the other side of the black hole, you have second CFT. In the left side, you have a second CFT whose Hilbert space is denoted as HBL. So you take these two Hilbert spaces and consider a specific state that is an entangled, that basically a state that is entangled, so that entangles the left CFT and the right CFT, and that state is dual to this eternal black hole geometry. Okay. So once we have this duality, you can do the reconstruction, but if you are looking at a particular boundary region, there is a maximum bulk region that you can reconstruct. And the maximum bulk region that can be reconstructed from a given boundary region is called the entanglement wedge of that boundary region. So for instance, if you look at the right side of the black hole, you see that the entanglement wedge is given by the triangle in the right side, the triangle that is shaded with light green. So if you are given any field in that triangle, that can be reconstructed using the operators that is living in the right boundary. So you just need one CFT to do the reconstruction of operators or fields that is living in the right side of the black hole. So similarly, if you look at a bulk field that is living in the left side of the black hole, then you just require the CFT in the left side. Okay. And if you're just if you're interested in a smaller region, and say in the right boundary, a smaller region denoted as N, then you will be able to reconstruct only the operators that is living in this dark shaded region, the region which is shaded with dark green. You take any operator there that can be reconstructed using the boundary operators that is living in the region N. Okay. Now, if you are interested in the interior of the black hole, then it's clear that just by looking at one CFT, right CFT or left CFT, you won't be able to reconstruct any operator that is, or any bulk field that is living inside the horizon. So if you want to construct the interior of the black hole or any bulk field that is living in the interior, you require both the left and right CFT. And that is because of the fact that the bulk interior belongs to the entanglement wedge of both the left and the right boundaries. Okay. If you have any confusions or questions, you can ask. Okay.
Yeah, doesn't seem to be any.
Yeah.
Doesn't seem to be any questions in the chat as well.
Okay, thanks. Now let us look into the PR and LL proposal for an eternal black hole. So the claim of PR and LL proposal is that even if you have a one-sided black hole, you can reconstruct the interior of the black hole. So if you go back and see this picture again, it's like saying that you have a black hole which does not have two sides. You have only one side and you have only one CFT. And the claim is that you can do the reconstruction of the interior of that black hole just using a single CFT. Okay.
Hi, Rosie.
Yeah.
Yeah. So can you reconstruct the entire interior of the black hole using the entanglement wedge? I mean, can you cover the full interior in this fashion?
For the eternal black hole or the?
For the eternal black hole. Because you're saying that,
yeah.
That the black hole interior belongs to the entanglement wedge of both the left and the right boundaries, right?
Yeah. So in principle, yeah, it should be possible.
Okay.
Yeah.
Thank you.
Yeah, thanks. Okay. So so like I said, the claim by PR and LL is that even if you have a single-sided black hole, you should be able to reconstruct the entire interior with the CFT that is dual to that black hole. But one thing to remember or note is that even for PR proposal, you have to you approximate the one-sided black hole with a two-sided black hole. Okay, and now if you look at the eternal black hole, you see that once you go to eternal black hole, even both PR and LL proposal requires the CFTs in the right and left in the following way. So if you want to construct the mirror operator, although the mirror operator is supposed to belong only to the right CFT, the construction really depends on the entanglement structure of the left and right CFTs. So it actually depends on the state of the entangled state of the CFT. Similarly, even for the LL proposal, you have to perform a non-trivial transformation called half-sided translation or half-sided modular transformation, and that half-sided modular transformation is constructed using the so-called modular operator. I will talk about modular operator later, but just remember that the modular operator, even if you compute a modular operator associated to a region in the right side, that modular operator can act both in the left and right CFTs. So even the LL proposal actually requires two sides of the CFTs in two sides. Okay, that actually matches with the entanglement wedge reconstruction program. So both proposal reconstruct bulk fields inside the entanglement wedge. It's not constructing anything beyond the entanglement wedge for the eternal black hole. So this is an important thing to remember. So the all.
But can I ask? So here, entanglement wedge, you mean just causal wedge? I mean, since you are using both the boundaries.
Yeah.
You mean the causal wedge? Right?
No, I mean the complete interior also.
Right, but if you use both the boundaries, then you
it can.
using, so that is then right. Just
right.
Causal evolution, you would be.
Yeah, actually, in this case, I think entanglement wedge matches with the causal wedge.
Okay.
Whatever I have drawn.
Thank you.
Yeah. We will see that a non-trivial thing will happen, like for more interesting setup.
Okay.
Okay. Which will be more than the causal wedge. Okay. So the thing to remember is that if you want to do reconstruction, whatever is your proposal, you will be able to do the reconstruction only in the entanglement wedge. So now let us look into a more interesting situation where we have an eternal black hole that is coupled to a bath. So here is the setup. You have the eternal black hole here, which has two sides, right side and left side, and you couple a bath in both sides. You couple a right bath to the right boundary of the eternal black hole and a left path to the left boundary of the eternal black hole. So by that, what he means is you remove the reflecting boundary condition that we impose for the case of eternal black hole, and we replace it with a transparent boundary condition. So then more interesting thing will happen. So we know that a black hole always emit Hawking quanta. So the moment you remove that reflecting boundary condition and replace it with a transparent boundary condition, Hawking quanta from the right side and the left side of the black hole will go to the right path and left path. So the moment it crosses the boundary of the path, the energy of the black hole decreases. So the bath, since the bath you have coupled have the same temperature as that of the black hole. So that's the kind of bath we are using. So we couple a black hole having a particular temperature to a bath having same temperature. So the moment Hawking quanta crosses the intersection of bath and the black hole, the gravitational region, immediately bath will send equal amount of quanta to the black hole. And also the bath that I'm discussing is a non-gravitating path. There is no gravity, non-trivial gravity in the path. So the moment Hawking quanta escape the black hole to bath, immediately bath will return same amount of quanta to the black hole. So, and there is an equilibrium. So there is no net flow of energy across the intersection, the boundary between the black hole and the bath. So that means that the classical geometry of the black hole is not going to change. So the current situation, an eternal black hole coupled to a bath, looks exactly same as a eternal black hole, which is not coupled to any bath. So the only difference is that in the eternal case, you have the Hawking quanta going to the boundary and then just get reflected back to the black hole. Here, instead of reflecting back, bath provides the quanta. Okay. So the classical geometry is not going to change. But quantum mechanically, there is an interesting phenomena happening. So the process of sharing quanta gives rise to a linear increase in entanglement entropy between the black hole and bath with respect to the boundary time. So there is an entanglement building between the black hole and the bath. Although the classical geometry is not changing, you have an entanglement building between black hole and bath. One can calculate this entropy. One can calculate the entropy of bath by integrating out the path degree, black hole degrees of freedom, and one can calculate the entropy of the radius density matrix. And it's not difficult to see that. I haven't shown you the calculation, but just believe me, it can it actually increases linearly with respect to the boundary time. So you can see here. So the plot. The x-axis is the boundary time, and the y-axis is the bath entropy. The entropy linearly increases. But after some time, a non-trivial thing happens. The black hole system has a finite amount of thermodynamic entropy, and it cannot. So the bath entropy cannot increase beyond that. So the moment it increases beyond that, the entire process is non-unitary. So there is a non-trivial information paradox even in this such simple-looking setup. So so there is a time at which the entropy of bath becomes equal to the entropy of the black hole, and that's the pace-time. So after pace-time, there's somehow some non-trivial thing should happen and make sure that the entropy of the bath won't increase beyond the upper or the maximum permitted value. Okay. So to resolve this paradox, so maybe before that, any questions? Okay. So to resolve this paradox, what one can do is we can revisit the path integral computation of entanglement entropy. So we just go back and see what kind of computation that we did to find the entropy of bath, and see whether that computation itself requires some correction or not. So the maybe I'll just revise or just quickly go through the calculation that gives the linear growth of entropy. So what you do is you just consider the Euclidean version of the geometry that we have. So we consider
Really,
the,
sorry, can I ask a question about the previous previous
yeah,
curve? So if we the linearly rising curve is the same curve you get if you look at the entanglement of the radiation with the Hawking quanta which are inside the horizon, right? Like the so somehow the fact that the bath, I mean, but this is telling us that this is not enough to conclude the bath has the somehow the same bath is a model for the interior yet, right? Even though the entanglement rising entanglement entropy curve is the same for the entanglement of the radiation and the interior quanta. Is same as this curve, which is the entanglement between the bath and the radiation, right? In your case, this is the entanglement between the bath and the
bath and
I thought in the usual information paradox, this is the same curve that is telling you that the entanglement is rising between the interior and the
right.
But that this is not enough to conclude that bath is a model for the interior, right? In any sense, I mean, I don't know. It's a very precise question. I just
so the additional quanta that you get are actually the in that case, I think since if you have a bath at 0 temperature, it's not giving back anything.
Yeah. I was saying that the usual paradox, this curve is telling you the entanglement between the radiation and the interior.
So here actually
the bath, but that is not enough to conclude bath is a model.
Right. So here actually the entanglement is with the the entire black hole, both right and left side of the black hole and the bath.
Okay. I said okay.
So far I haven't said anything like particularly the Hawking quanta that is going inside the black hole is entangled with the bath. I haven't said anything like that. I'm just saying that since there is an exchange of degrees of freedom of bath and the black hole, there is an entanglement building between the two-sided black hole and two sides of the bath.
Okay. Thank you.
Okay. Thanks. Okay, so we will quickly go through the replica calculation. So what we do is we consider the Euclidean version of black hole and black hole coupled to bath. So that's given by a complex plane with a disk in it. So inside the disk, the blue shaded region is the black hole region or the gravitational region, and outside the yellow region is the bath region where there is no gravity. And then what we do is we take this Euclidean geometry and make cuts along the bath region. So actually I should have made cut in both sides, but just to remove the cluttering, I just made a cut in one side. So you cut the complex plane outside the gravitational region and take such n copies of complex plane with a cut in it and identify the cuts in a cyclic way. So basically the lower cut of one sheet will be identified to the upper cut of the nearby sheet. So you do this cyclically, and this gluing give you a glued path integral. Okay, so this can be understood as doing a CFT partition function calculation on a geometry obtained by gluing this n copies of Euclidean geometries. Okay, and this log of the partition function of CFT computed on this geometry give you the Rayleigh entropy, nth Rayleigh entropy, and after taking the appropriate limit, you get the entanglement entropy. So the basic thing that we do is we consider Euclidean geometries and glue them, and then do CFT path integral. Okay. But the moment you have gravitational region in your space-time or in your Euclidean geometry, then the path integral gluing is more involved. And that's because of the fact that if you glue a set of gravitational region, you cannot just by looking at it say what is the geometry after gluing. So because Einstein's theory says that you have to always solve the Einstein's equation to find classical geometries or classical spacetimes. So the gravity demands us to solve the Einstein's equation and find a smooth solution satisfying the replica boundary condition before evaluating the matter path integral. So we do this gluing in the non-gravitating region, and then the Einstein's equation should decide what happens in the gravitation region. So there are different things that can happen. One is the first setup, first situation, which is a Hawking saddle. So where you have the usual gluing like that you do in the in any quantum field theory where there is no gravity present. You take n copies and just identify along the cuts. But there is a non-trivial solution also. So that has connections between different gravitating regions. Okay, so there is a connection having a topology of a sphere with n number of holes. So that's the wormhole saddle. Similarly, you can have another saddle which has handles in it. So there are many such saddles possible. Okay. So the complete answer involves a sum over all the gravity saddles. So it includes the Hawking saddle, the first wormhole saddle, second wormhole saddle, everything. Now, the non-trivial thing happens after spacetime. So after spacetime, what happens is that the path integral, the CFT path integral that you compute using the Hawking saddle has more value, or it is suppressed compared to the wormhole saddle, the CFT path integral that you perform on a wormhole saddle. So after spacetime, the dominant contribution is coming from not from the Hawking saddle, but it's coming from a wormhole saddle, which has a bridge connecting all the different copies of the replica. So, for instance, if you consider the wormhole saddle, so you see that there is a sphere connecting, let's say here, 4 gravitation regions. And so the entire replica path integral has a nice cyclisymmetry. So there is an Z4 symmetry here. So when you compute path integral, you quotient the symmetry, and then you see that the C4 action has two non-trivial fixed points. So one here and one on the other side of the sphere. Okay. So these fixed points has a nice interpretation. So from the holographic entropy calculation. So these fixed points are the RT surfaces, or the quantum corrected RT surface, or quantum extremal surfaces. Okay, so when you compute a CFT partition function, you will see that at this point you have a non-trivial monodromy, and you have to introduce a twist field here there. And from the holographic point of view, it just says that there is a non-trivial RT surface or quantum extremal surface there. Okay. Now, the definition of entanglement wedge is that it is the region enclosed by quantum extremal surface. So here we see that the moment you go to the wormhole saddle, you will start seeing non-trivial quantum extremal surfaces or non-trivial quantum corrected RT surfaces. So that is equivalent to saying that when you go back to the Lorentzian picture, you will see that there is a region inside the black hole that belongs to the entanglement wedge of the bath. Okay, so that red region is called island for bath, the bath island. So physically, what it means is that if you want to construct any field that is inside the bath island, you should be using the degrees of freedom in bath, not the degrees of freedom or not the operator that belongs to the CFT, which is dual to the eternal black hole. So here you can assume that there is a CFT living at the boundary of eternal black hole, which is coupled to some other system, which is basically the bath. So if you just look at the CFT that is dual to the eternal geometry and try to do a reconstruction inside this island, you won't be able to do it. You should not be able to do it. So, and if you want to do a reconstruction, you should be able to do it only using the CFT that is living in bath. Okay. So,
Sorry,
Roji,
yeah. Go on.
So Roji, I just want to check. So in the theory on the ADS space, are you considering some particular matter content, or what is it that you're doing?
So I'm just, I mean, so far I haven't considered what I just consider as conformal field theory. That's it.
A CFT in the bulk, you mean? Is that right?
Yeah, even in the bulk. Yeah, that's
Okay.
just to make the calculation easy.
Okay.
So you have several CFTs. You have a CFT living in the bulk and
Uh-huh.
a dual CFT at the boundary.
Okay.
and a bath which has same CFT that is defined in the bulk.
I see. Okay.
All these are just to make the computation simpler.
So these saddles you mentioned are when you do the bulk computation with a particular CFT. Is that correct?
Yeah.
Okay.
So, Roji, so the first line in the slide, I mean, in general, that's like a proposal. I mean, this line itself is not just about 2D gravity, right? The fact that after page time, some other saddles dominate. So this is a proposal that we check in some models.
The point is that, we have to look at all saddles. After computation only, we know that whether that saddle dominates or not.
Right. But the fact that this, the fact that, as you were saying, that these other topologies, the wormhole type topologies dominate, that is, I mean, that has been checked in some low dimensional 2D gravity, but in general, it's a proposal that one should.
Yeah, the basic, maybe one can try to understand it. Naive argument is that if you consider the trace of rho square,
right,
then if you're computing in the Hawking saddle, so that is a non-trivial object. Now, if you compute that in the baths, so in the wormhole geometry, it so happens that it becomes a trace of rho square becomes trace of rho whole square. So that the contribution from CFT will be suppressed and the contribution from the RT surface or the quantum gravity will be dominated. So in the previous case, what happens in the Hawking saddle is that the contribution from the CFT just grows. It is linearly increasing. So you somehow want to cure that linear increase of even the partition function is keep on increasing from the CFT side. So you just want to control that. So the moment you go to the wormhole geometry, that will be controlled.
Right. But I'm asking that this is, if I think of what you're saying as a scenario, then the scenario has been realized in some models, but
lower dimension
scenario in higher dimension. Also, we should consider the scenario. That's
if somebody tells me this is a blind rule, it's not something which I can accept. Only after doing the calculation, we can accept it. Right? Okay.
And the other thing is this, as you are saying that once the bath, this once the Z4 action gives you the fixed point and you have this bath island contribution, as you are saying that then it is not enough to construct the boundary CFT is not enough to construct the interior operator.
Exactly.
So if we did not have if we had just the original eternal black hole, we could have used the Suvrat or the Honglu proposal to construct interior. But now once as you're saying that as the islands form, then we have to
it's not. I'm not saying that the LL proposal or the Suvrat proposal will fail. I'm just saying that you have to appropriately modify it.
Yeah, that's what I'm asking. Yeah, exactly. That's the picture you're
right.
Okay, thanks.
Yeah. So the only thing is that if I apply LL proposal or Suvrat proposal to the dual CFT.
Yes.
Dual to the eternal black hole, then that should fail.
Right. When you look at this non-trivial saddle in the
when I look at a non-trivial saddle, basically after page time.
Okay. Thank
you. Yeah.
So Roji.
Yeah.
So you are saying it would fail when you don't have these bath CFTs, right?
Sorry.
You're saying that those proposals would fail when the bath CFTs are not there. Is that
no? If bath CFT is not there, there is no issue because entanglement wedge is always with the CFT, which is dual to the eternal geometry. Hello.
So Roji, can I just restate? So you're saying that because the presence of the islands somehow necessitated a breakdown of this.
It should break down. Basically, that's the expectation. All the maximum reconstruction that you can do is within the entanglement wedge. Okay. Now maybe you can say in another way. We should check whether the LL proposal and RR the PR proposal, the Papadodimos strategy proposal, whether it is reproducing the entanglement wedge calculation that we have done here. So that is, maybe one can think of that as a check of their construction.
All right, I understand. Thanks.
So if they have a right bulk reconstruction which satisfies the entanglement wedge reconstruction program, then just from the bulk reconstruction, we should be able to see the emergence of these islands. Okay. So that is for the consistency of that's basically a consistency check of their construction.
Okay, thanks.
If that is not happening, then we should understand all this entanglement mesh reconstruction proposal again. So the that will include the quantum error correction program, right? So if you know that Subrat and Liu Littenser proposal is successful even beyond the entanglement wedge, then we have to go back and see what is happening in the quantum error correction.
Right.
Or we should say we should find a fault in the reconstructed operator.
Okay, thanks.
Yeah.
Hi,
So
Roji.
yeah.
I just want to continue.
Hello. Sorry, I'm not able to hear you.
I think you
Hello?
can I can continue, Roji. He's got disconnected, I think. Yeah,
Okay.
yeah.
Okay, fine. So like I already discussed, given that we have the proposals for black hole interior reconstruction, we should be able to derive this fact that we won't be able to do the reconstruction from the CFT dual to eternal black hole after space-time. So we should be able to see this fact from the explicit reconstruction. So we should, more precisely, we should be able to see the breakdown of interior reconstruction after space-time just by using dual CFT. Okay, so there are two ways, or there are maybe these are the two ways in which the entire thing may break down. So after space-time. So for the case of Subrat and Papadodimus construction, maybe that after space-time we may not be able to construct mirror operators.
Hi,
That
Roji.
might-
Sorry,
yeah.
hi, Roji. Can you hear me
Yeah.
now?
Yeah, I can
Yeah.
hear you now.
I'm sorry, somehow it got disconnected. Yeah,
Okay.
I just wanted to ask, so the path is essentially just accounting for the entanglement entropy, right?
Right.
It plays no non-trivial role as such in the island scenario.
I mean, so we won't be having an island if you don't have the path.
Okay.
So if you remove the path, then there is no exchange of Hawking quanta and Bath quanta. Basically, this is a exchange of Hawking quanta and Bath quanta is the one that give rise to this linearly increasing entanglement. Otherwise, the entanglement is always fixed. There is no
Okay,
rise of entanglement.
we can go back to this question later. Thank you.
Okay, thanks. Okay, so so the thing is to see whether there is, there is one way to check is like if you want to check Subrat proposal, you should be able to see or might be able to see a failure to reconstruct or failure to construct the mirror operator, which is essential for doing reconstruction of operators inside the horizon using Subrat proposal. And if you are following LL proposal, Literature proposal, then we should be somehow able to see that the half-shaded modular translation that you perform in the bulk, the boundary dual, the dual CFT of eternal black hole should become trivial after the space-time. So one or the other, like we should be able to see this. So so we have two proposals. One proposal depends on mirror operator. In that proposal, maybe after space-time, the construction of mirror operator may fail after a space-time. And for the case of the LL proposal, maybe the half-shaded modular translation becomes trivial after space-time. And in this talk, we will only focus on LL proposal, the Liu-Little proposal. And what we will try is that we will try to argue that the space-time, after space-time, the half-shaded modular translation has no non-trivial action on the dual operator. So in the following slides, we will be discussing more about the LL proposal, and we'll discuss more about half-shaded translations. So in case if you have anything to ask, maybe.
Hey, Roji, one small question. Could I ask this in a reverse way, that if I just think of can I use the bulk reconstruction inside the horizon as a diagnostic for wormhole formation? Like I do a bulk reconstruction. If it fails inside, that means that the interior geometry is somehow not smooth or something. So something non-trivial has happened. Like, right? I mean, could I reinterpret this question in that way, that I use these two proposals, and if they break down or something non-trivial happen, means the interior geometry, which I assume to be smooth, is no longer some branch
Uh,
got developed or something. I mean, some wormhole is been
Right.
created. Or is that not a right way to? I mean, formulate this.
Yeah, actually, the way in which I thought was that you do the reconstruction and see, like, see, when you do the reconstruction, we don't really take into account the complete quantum corrections and all. You do only reconstruction for the leading,
Correct.
the
Correct.
classical part, right?
Yeah.
So what I take is that after phase time, the classical part is no longer the Hawking saddle. So even from the bulk reconstruction, we should be able to see it. So
Exactly.
It's not,
So that's the point, right? Like bulk
Right.
reconstruction is a diagnostic for
yeah,
breakdown of the classical.
right. So instead, yeah, exactly like you said, instead of depending on the entanglement entropy calculation, you do the bulk reconstruction, then
Right.
see which is the leading contribution to the entire reconstruction and call that as the correct reconstruction procedure.
Okay. Okay. Thanks.
So it's no way like mixing these two, like
Yeah.
do bulk reconstruction completely and then somehow find a transition and then see that there is a breakdown of reconstruction.
Yeah. Okay. Thank you.
Yeah. So this entire thing doesn't depend on what we want to do is we don't want to rely on any theorem or anything. We just want to simply do a reconstruction and see whether what actually happens.
Right.
And we should be able to find the island just from the reconstruction. Okay. So we will talk more about the LL proposal, and the LL proposal is based on the algebraic quantum field theory idea, the half-sided modular translation. So, so half-sided modular translation is an interesting operation that you perform in quantum field theory, and that is constructed using another operator, another interesting set of operators called modular operators. So you have a special kind of operators in quantum field theory, which are called modular operators. You take those modular operators and one can construct a kind of a special transformation, and those are the half-sided modular transformation. We'll get into more details of both modular operators and the half-sided modular translation. So again, as I already told you, like my algebraic quantum field theory background is not that much, and I'm not much interested in going into the mathematical details. So when I say all this von Neumann algebra and all those things, just think that there is a bunch of operators that you have. So you have, let's say you have a von Neumann operator algebra, which I call a calligraphic M, and the operator that belongs to this algebra, they act on a Hilbert space denoted by H. So you have a bunch of operators that's acting on a Hilbert space. And in that combination, once you have this combination, this operator algebra and the Hilbert space, you can find a very interesting state in the Hilbert space, which has a property that you take any operator in the operator algebra M and act on the state omega. The state won't be annihilated. Okay. And also it has a property that you take the state and consider all the operators in the operator algebra and act on it. So take one by one the operators from the operator algebra and act on the state omega. You should be able to get the full Hilbert space. So usually they say dense subspace in the Hilbert space. So forget about all this dense. Just you are able to you will be able to construct the Hilbert space. Okay. If you are able to find such a state, then that state is called a cyclic and separating state for the operator algebra M. So it's just a special kind of state, a state which is not annihilated by any of the operator that belongs to the operator algebra. And also, if you want to construct the entire Hilbert space just by using this ladder operation, you can, like we see in the harmonic oscillator case, you can take the operators from the operator algebra and act on the state omega and construct the entire Hilbert space. Okay. So given that such a pair, a von Neumann algebra M and a state omega, we can then define a special operator called the modular operator. So you have a von Neumann algebra having a cyclic and separating vector. Given that, you can construct another operator called a modular operator. This modular operator has a property that it's actually a symmetry of the operator algebra. You take this modular operator, act on any operator in the von Neumann algebra, that will give you back another operator that again belongs to the same operator algebra. So it is like a permutation kind of operator. So take the modular operator, act on any of the operator in the operator algebra, that will give you another operator, which is again in the operator algebra. And also, you take the modular operator and act on the cyclic and separating vector. It will keep the cyclic and separating state invariant. So action of delta m on omega will give you omega again.
So is the separating vector unique, or there can be more than one?
If you ask me all those things, I don't know. Maybe I don't know the any theorem. So I can't say anything. I'm just saying that if there is such a state, then that state, using that state, you can define another operator.
Okay.
Okay. Yeah.
Thanks.
Maybe I'll look and let you know.
Thanks.
So in case if anybody knows, they can tell.
Yeah, they would be, because those would be generating different super selection sectors.
I see. Okay. Thanks.
Thanks.
Anyway, so you have this interesting operator delta m, and the property of this operator is that this operator can act on the operator algebra m and also on another operator algebra m prime. So what is this m prime? M prime is called a commutant of m. Basically, it is a set of all operators that commutes with all the operators in the operator algebra m. Okay, so this is another operator algebra. If you take any operator in M prime and try to find a commutator with the operator in M, they will just commute. So such set of all operators forms the commutant of M, which we denote as M prime. So delta M not only acts on M, it also acts on the commutant M prime. That means and also, for more general case, the most general cases, the operator delta m cannot be factorized into two operators that separately acts on m and m prime. So there's a complicated operator, the modular operator. It acts both on m and m prime, and in general we can't expect that the action of, although the operators m and m prime commutes, the modular operator can't be in general factorized into a piece that acts only on m and another piece that acts only on m prime. And the log of this operator is the modal Hamiltonian. So take this modular operator and find the logarithm of it that give you the modal Hamiltonian. Okay. So now we have an operator algebra, and associated to that operator algebra, we have a modal Hamiltonian or a modular operator. Okay, so now we want to construct the half-sided translation. So what we do is we take this von Neumann algebra M and find a subalgebra of M, which we denote as N. So M is a subalgebra of N. And also demand that the cyclic and separating vector for n is again the same omega. So the cyclic and separating vector for both m and n should be same, and n should be a subspace of or subalgebra of M. Then we can construct another interesting operator, which is the one that generates a half-sided translation. So you take, consider this modular operators associated with n. We denote it as delta n here, and the modular operator associated with m is delta m. Okay. Now consider this particular combination: delta m raised to minus it into delta n raised to it. Okay. So this operator is a unitary operator, and which we denote as us. So the generator of that unitary operator is a positive operator. So it's basically e raised to minus igs. Now the parameter in the right side is t, and in the left side you have another parameter s. So they are connected. So the parameter s is given by e raised to minus 2 pi t minus 1. So the half-shaded translation can be constructed if you have two operator algebra. One is M and another one is a subalgebra of M, and that we denote as N. Then just take the modular operator, raise them to appropriate powers, and take a product of them. So that give you the operator that generates the half-shaded translation. And this half-shaded translation operator has some properties. We won't get into all those details. So I just want to let you know that this is the way in which you construct the operator that generates a half-shaded translation. Now, we can write down the generator of half-shaded translation in terms of the modular Hamiltonian associated with operator algebra M and N. So what you have to do is you just use this relation between S and T. S is given by e raised to minus 2 pi t minus 1. And in the left side, you have e raised to minus es. On the right side, you have this product, delta m raised to minus it, delta n raised to it. And I already told you that delta m is e raised to minus km, where km is the modal Hamiltonian. And delta n is e raised to minus kn. And kn is the modal Hamiltonian associated with the algebra n. Now, you take small values of t and expand both sides to linear order. And from there, by matching order by order, we can find that km minus kn is the generator of the half-shaded translation. Okay.
Sorry, Roji, since I don't know any of these things at all.
Yeah, sure.
I just take like free field theory. Can you give me what is the modular Hamiltonian here, for instance?
Free field theory, like the modal Hamiltonian is a boost operator, like if you are in Minkowski spacetime.
Okay. Okay.
Yeah, so for simple cases, we can actually find this operator.
Okay.
Yeah.
Thanks.
Okay. And I will actually discuss the case of Minkowski spacetime in the next slide. So things will be clear there. Actually, I don't want to just follow all this algebraic quantum field theory setup. We want to do this in a simple setup so that we can actually understand what is going on.
Okay, great.
So that will be doing in the that I will discuss in the next slide. Okay, one more theorem.
Just one question that actually this, as you are explaining that this, I mean, whether from quantum field theory perspective, whether it's a von Neumann algebra or not is not important, right? The fact that if you have some boost generator or this modular Hamiltonian,
Yeah,
you can
so,
use them to construct
right.
this G. I mean, you don't.
I will mention about that.
Yeah.
That's the next line.
Okay.
So there's a theorem that says that you can have half-sided modular translation only if the operator algebra M that we consider is a type 3-1 von Neumann algebra. So don't ask me about the mathematical details of type 3-1. What I can say is that if you take that operator algebra M and find its modal Hamiltonian, it should have continuous spectrum consisting of all real numbers. And the boost operator that you mentioned now actually has that property. So most of the time, what we are dealing with is type 3-1 von Neumann algebra. So the moment, like you said, we have a boost operator that actually satisfies the type 3-1 condition.
Yeah, I think this just says that this only exists in relativistic quantum field theory. That's all.
Mean, I don't, yeah. So anyway, I'm not bothered about that.
Yeah, I know, but I think that's the content.
Yeah, that's the content. Okay, good. So anyway, like I'm working working with only that kind of simple setup. So I can safely assume that whatever construction that I have will hold in the kind of quantum field theory that I deal with. Okay, so all this existence theorem, like that, anyway, algebraic quantum field theories will do. So we just want to understand the meaning of all this construction. What does it mean? How actually this is realized in a simple conformal field theory. Okay, and we want to see whether this whole construction is simple enough to answer the question in which we are interested. So we want to understand that when you have black hole coupled to a path, there is this building of entanglement and there is a non-trivial island formation. So we just want to know whether the proposal by Honglu and Luther is simple enough to understand that setup, so that we can explicitly do the bulk reconstruction and see the formation of an island. Okay, so we just want to get rid of all these complicated jargons. So that's what we are going to do now. Okay, so we want to understand what do you mean by a half-sided translation in Minkowski-Rendler spacetime. So we will be considering the simplest case. Take a two-dimensional Minkowski spacetime and define a conformal field theory having central charge C and stress tensor T++ and T minus minus. And assume that this theory has a scalar field phi, because we will be interested in the reconstruction of this scalar field. So that is the easiest one. So you take a CFT. I'm not assuming anything about the CFT. I'm just assuming that it has a central charge and it has a stress tensor T++ and T minus minus, and the CFT has a scalar field. So nothing more about whether this is a free theory or anything. Okay, so now look at this picture. So we have the Penrose diagram for Minkowski, two-dimensional Minkowski spacetime. And I have divided this spacetime into different patches. So in the right side, you see a patch that is denoted as M. So this much, the entire right wedge, that is the right Rendler wedge. And similarly, you have a left Rendler wedge, and you have a region that is in the future and the past. So this setup is very much very close to a black hole geometry, very close to a black hole geometry. So we want to understand what is happening in this simple setup. So we take a CFT in this spacetime and find or define a algebra observable that is associated with the right Rendler wedge as M. So our M is the set of all operators that is living in the right Rendler wedge. So that algebra observable is called M. And now we also consider a subalgebra, so which is a sub-region, a region inside the right Rendler wedge. So that's given by this smaller rectangle, so which is denoted as N. So we consider all the operator or observables living in this region N, and the algebra observable is associated with the subregion of the right Rendler wedge is the subalgebra N. And the cyclic and separating state omega is simply the Minkowski vacuum. Okay, so this is a setup. Now we want to see what is the modular translation. Can we construct an operator that actually does this half-sided translation or not? So we just want to take this field, scalar field phi, and act with the modular or half-sided modular operator. So we want to see the half-sided modular evolution of this simple scalar field in this geometry. And I already mentioned what is my M and what is my N. So given that, we can construct US, and US is given by delta M raised to minus IT and delta N raised to IT. So take this field and act with U dagger from the left side and U from the right side. And that give me the operator phi of S, X plus X minus. So we want to understand what is this evolved operator. Okay. Now,
can I ask a question?
Sure.
Yeah, so in the previous slide, you mentioned that you have this algebra M and M prime, which correspond to the two different Rendler wedges. Right. Can you explain what is in flat space? What does it mean for algebra of observables in the right Rendler wedge? Yeah, so so you want to say more about the algebra observable M? Yeah, in the sense in ADS, you just use this normalizable, non-normalizable kind of thing to define, I suppose. But in flat space, how do you define them?
No, this is a bulk region.
It's just in the bulk. Yeah, just the bulk region. I'm not worried about the boundary.
M is. I see. M is the full Rendler.
M is the full Rendler wedge. Right.
I see. Okay.
It's not the region in the future infinity.
I see. Okay.
Yeah. So there's nothing in the sky plus, it's just the entire thing in the bulk, entire thing in the right Rendler wedge. And yeah, maybe like just to, since you mentioned it, the M prime, which is the commutant of M, is the causally disconnected region in the Rendler space, in the Minkowski space for the right Rendler wedge, which is basically the left Rendler wedge. So the right triangular wedge is the if you consider the operator algebra in the right triangular wedge, then the commutant of M is M prime, that is the operators living in the left triangular wedge. They can't, they always commute, right? Similarly, if you take the N, then there is an N prime here. Again, just by using the causal disconnectedness, you can find the region, and then you can find what is the operator algebra, which is the commutant of N. Okay, so the complicated jargons just means this.
Okay.
Okay, so you take the evolved operator, and we want to understand this evolution. Okay, unlike in the general case, so I said that in general case, modular operator cannot be factorized into a piece that acts only on the operator algebra M, and another piece which just act on the M prime or the commutant. So for the simplest case that we are considering, it is possible to do this decomposition. You can consider a part that just acts on the right triangular wedge and the left triangular wedge. So the delta M can be, which is a modular operator for the right triangular wedge, can be factorized into two pieces. One piece is acting only on the right triangular wedge, and the other piece is acting only on the left triangular wedge. And the delta M hat, the delta M bar can be understood as the reduced density matrix for a state that is restricted to live in the right triangular wedge. And delta M inverse can be understood as a reduced density matrix that is restricted to which is a restriction of a state in the Cauchy slice to the left triangular wedge. So the modular operator is basically related to the density matrix, reduced density matrix. Okay. So now we want to use path integrals to get a better understanding of all the setup, all the operators. So the bulk, the path integral representation of delta M bar is given by the CFT path integral in a plane with a cut that starts from PM. So PM is the center, or the place where it's basically the bifurcation point where the right triangular wedge and the left triangular wedge meets. So the path integral representation for delta bar M, basically that is a part of or piece in the modular operator that only acts on the right triangular wedge. So that is given by a path integral, a CFT path integral in a plane with a cut from point PM to infinity, and the angular direction is clockwise. So this wedge, the wedge with a light green shade, so that is a path integral representation of delta bar M raised to IT. Okay, so where the angle of this wedge is theta given by IT. Okay, it's a complex angle. So the Euclidean path integral representation is given by a wedge for delta M raised to IT. If you set t to be 2 pi, you get back the modular operator delta bar M. Okay. Now, similarly, for delta hat M, the path integral is given by a wedge in the other side with angle again theta equal to IT. Okay. So when you're doing a correlation function calculation, let's say involving the scalar field phi, now you want to see what is the correlation function after evolving this scalar field phi using this half-sided translation or modular operator. What you should do is you should be just introducing wedges in the appropriate places. So you just take this wedge, path integral wedge, and introduce this wedge in the path integral, which corresponds to the correlation function calculation. Okay. So introducing wedges in the path integral is same as introducing the operator delta MIT. So you introduce these two wedges, that is equivalent to introducing this operator delta M raised to IT in your calculation. Okay. So any confusions or anything you want to discuss? Okay. So Now, introducing a wedge in the path integral for a CFT can be replaced by a conical twist field. So this is a special field in your theory, and that can be constructed using the stress tensor. Okay, so you just take the stress tensor, multiply it with z minus zpm. Zpm is the coordinate of the bifurcation point pm, and then multiply that with stress tensor and take dz, and then consider the complex conjugate piece. And there is one more piece which is c by 12. C is the central charge of the CFT, and then dz divided by z minus zpm. So this second piece, z by c by 12 into dz by z minus zp. So that piece has the role of introducing a conical excess angle in your path integral. And you take this combination and then integrate the operator from the bifurcation point to infinity. So that is the generator of this modular translation, or basically that can be understood as the modular Hamiltonian. And if you want to introduce a wedge having angle theta, then you should be just considering e raised to theta qm, where qm is this integral, which runs from pm to infinity. So the modular operator raised to it can be understood as or replaced by a conical twist field. So if you want to find a half-sided modular evolved operator,
Roji, can I ask maybe one silly question? So if I, as you said, that the delta is really the density matrix obtained by tracing over the complement, like if I take a Cauchy slice, right? And then I would have thought then so this is like rho to the theta, as you explained, right? Like
right.
But rho is like e to the minus beta h, where I would have thought beta is the temperature of the Rindler observer for the wedge m. But here I'm not able to see that representation of the density. Maybe I just missed something.
See the point. So for that case, I think it will be the boost operator, right? The Hamiltonian will be the boost operator, and this is actually a boost operator.
But then the beta should be the. I mean, okay, maybe the somehow there should be some temperature for the density matrix, right? I mean, or that doesn't show up here. Maybe okay, maybe it's not right. Maybe I'm just we can discuss later. Yeah.
Right. I think if you right. So if you want so in the map, if there is the temperature, that will be appearing with this theta.
Okay. I see. Okay. You just right now said 2-1.
Yeah, I just said 2-1. Okay. So that can be absorbed in this parameter. Then so because I haven't mentioned the acceleration.
Yeah.
So anyway, so the half-sided modular evolved operator phi of s can be then understood as operator phi acted with this conical twist field from both sides. Nu theta pm, nu minus theta pn from one side, and the other side nu minus theta pm, nu theta pn. Okay, so this is a non-local operator, the conical twist field operator. So in path integral, what you do is if you have us dagger phi us, which is the modular evolved operator, then the calculation that you have to do is you just take this operator phi and then add this conical twist field, which is basically which involves an integral over a contour. So the nu minus theta pn is an operator that involves an integral along the contour which starts from pn to infinity, and that goes below, or that runs below this operator phi. And the one that comes with for delta n, that is comes with us dagger, that will come in the upper side. Similarly for nu theta pm, so you have to enclose this operator in these contours. Since so acting an operator from two sides can be understood as a contour integral, right? And if you use the OPs. So we have to just understand this contour integral. Okay, so yeah. Now, So you have two contour integrals. One is associated with the delta n, and the other one is associated with the delta m, or nu pm or nu pn. And we know what is the operator that with which we have to take the OP. Like you have the TC in the exponential. So what at the end, this calculation just requires you to know the OP between T, the stress tensor, and the scalar field phi. So this can be easily evaluated, and you can actually see that. So the resulting evolution is a combination of two boost operations. So that I will explain in the coming slides. So anyway, so you have two contour integrals coming in two sides. So if you want to take this field out, or basically if you want to act with this operator, what you have to do is you have to just evaluate this contour integral. So you have two contour integrals, and one contour integral is associated with this operator e raised to theta qm. Other one is associated with e raised to minus theta qn. So so when you have product of two such exponential operator, what one can do is sometimes we can combine this product operator and get an effective operator using this Baker-Campbell Hausdorff formula. So for that, what we need is, so basically what we want to do is we want to find the simple form of this modular half-shaded modular operator. So we use the general formula and then so that it is a product of two conical twist field. We want to find the effective field that you obtain after taking product of two conical twist field, and that can be computed using the BCH, a special case of BCH formula. So for that we need to note that, so this nu theta pm, when if you are only interested in acting on this field phi, can be although this involves integral from pm to infinity. So if you are acting nu theta from two sides, this can be replaced with a contour integral around the point P where you have inserted the operator phi. So effectively, if you are only interested in acting on this operator phi, the nu theta pm can be replaced with exponential of same operator integrated along a contour that encloses the point where you have introduced the operator phi. So at the end, what you have is two simple contour integration. So the theta qm can be replaced with a contour integral around the point where you have inserted the operator phi. Now, once you have that, the entire qm has a simple form, and you can calculate the commutator between qn and qm, which is again given in terms of qn and qm. This is just the difference between qn and qm, the commutator. So given that, if you have such a relation, then there's a special case of Baker-Campbell formula that says that the operator us becomes e raised to s qn minus qm, where s is given by e raised to 2 pi I theta minus 1. And if you replace theta with t, then it's basically the same relation that we already had between us and the operator in modular operator involving the parameter t. So the relation between the parameters t and s we are able to reproduce using this conical twist field. So we see that us is basically e raised to s qn minus qn, and this means we can identify the generator of half-shaded modular translation, and that's given by qm minus qn, which is just a contour integral of Tc around the point P. And the effect of this is just to do a translation. Okay, so if you go back to the Minkowski picture, this operator, what it does is it actually translates the scalar field along the ingoing and outgoing direction, because the effective operator that we found is just P minus, which is doing translation along the x minus direction. Okay. So any confusion or doubts?
So Roji, the formal result you had in algebraic monofilament theory, which said that the US is defined as e to the GS, where IGS, where S is related to T. Like you have explicitly now shown that is true in this case.
That actually I can reproduce.
You
Right.
can just explicitly reproduce for a CFT in 2D with a Minkowski.
Exactly. So when I wrote, so we'll just go back and show you. So when I wrote this expression, so this is coming from some theorem. I don't know from where it
Yeah,
came.
yeah. Now you are explicitly displayed this from.
Yeah. For the simple case, I'm just reproducing it.
Okay, thanks.
Yeah, it might be that they are using a very complicated version of Baker-Campbell in more general quantum field theory. I don't know from where it actually comes. I just borrowed this result and I'm just showing you that in simple case you can reproduce it. So that actually tells you that the conical Tisp field is actually the modular operator.
Okay, thank you.
Yeah. Now, all this thing can be seen in a simple picture. So what is actually happening? So I said that if you are only acting the operator, the modular operator on a field inserted here, then the operator also takes a simple form. And the effect of that operator is just doing a boost. So you start from point P where you inserted the field phi and boost this along this trajectory. And what is this trajectory? So the Qn is basically the modular Hamiltonian associated with the region n, and n is here. Okay, and the trajectories of modular Hamiltonian in this region is given by this line, this dark line, which is basically we can think of that as a time evolution restricted to or boost restricted to this pink region. The property of this boost is that it keeps the tip of this pink region or Pn untouched. So this is a boost that does not change the tip of the region n. So you take and for the region m, the right innervation is actually a boost that does not affect the bifurcation point. So these are can be understood as kind of a time evolution. So you start with from the point P and act with the boost operator Qm that take you to another one point, this blue point, and then you act another boost in the opposite direction, the boost associated with the region n. So that take you back to to this point P prime. Now the result is that after doing this two boost transformation, what you did is you took the point 3P, the red point P to P prime, and which is simply the infalling. So geometrically, or what this half-circle translation is doing is it's taking a point P and then moving along the ingoing direction. And whether you're going in the ingoing direction or you're going in the outgoing direction, that just depends on the sign of the parameter S. If the parameter S is negative, then you will be going inside to the interior or to the region that is not accessible to the observer on the right side. Or if you're taking S to be the positive parameter, then you're just taking the point to the past infinity. So this is the way half-circle translation is doing the ingoing and outgoing. So maybe I'll stop here. So maybe in the next lecture, I will talk about the thing that is happening in the case of JT gravity and a setup where we have path attached to it. Okay, so if you have anything, you can ask me.
Okay, yeah, thanks. Thanks a lot, Roji, for the very nice talk. We still have 5 to 8 minutes. So if there are further questions, people can ask. Yeah, I think, there were many questions already during the talk. Maybe I can, I don't know if this is worth worrying about or not. Although you haven't talked about it today that much. So I guess at some point you will be talking about entropies and black hole entropy and page curve. Is that correct?
Yeah. So I don't want to calculate the entropy. What I want to show is that when I do this half-circle translation for the case of black hole attached to a bath, all this thing will naturally come. The space-time will naturally come. That you will see that the reconstruction has to be done in a wormhole geometry.
So to make sense of those entropies, you need to then use this cross product state like Wheaton's recent papers.
I haven't gone through them. What I can say is that I will just use this modular operator delta m, and so from there, like it should be possible to see it. I mean, none of this thing required like more than what I already told you.
Okay. No, I mean, I was simply wondering that if you actually need to go to those technical details, that when is the entropy correctly defined and so on, then it seems what they are suggesting that the algebra changes from to type to infinity and so on.
Maybe that's the underlying thing that is happening. So if you move from type 3.1 to something else, there is no half-sided translation.
Yeah, that's what I was going to say.
Yeah, so at the end, what I prove is that, or show is that, or what I attempt to show is that this operator US becomes an identity operator. That means that operator doesn't exist after page-time. So I don't know whether that is actually capturing the fact that after page-time there is a transition happening and the operator algebra changes. Maybe that's the underlying reason, but somehow like wormholes actually allow me to make or at least demonstrate that the half-sided translation become a trivial thing.
But Roji, your modular half-sided translation will continue to exist up to horizon, right? Like even in the, outside the horizon.
No, even in the horizon, up to horizon doesn't exist.
It won't exist.
No.
I see. Okay. That's why you're saying it would be.
Yeah. So maybe that such
that you will show in the next lecture.
Right. Half-sided translation can be done towards the interior or towards the exterior, like towards the sky minus.
So you see, it just won't exist once
it just won't exist inside the gravitational region.
I see.
Yeah.
One small thing that this result you showed, like in the Minkowski, it was not for generalized free field, for any CFT, right? So
this is for any CFT. I haven't used any.
So it's like it could be. I see.
Yeah. So the Honglu, what he does is he does not actually construct the. He's not interested in constructing the operator US itself. He was trying to see the action of US on a field. So for that, without constructing the US, he was using certain condition that US satisfy when it acts on a field. So he just used some bunch of conditions, general condition US is supposed to satisfy, and then just solve those conditions for a generalized free field.
Right.
So somebody was asking.
But your result is non-perturbative in that. In the sense your theory.
Yeah, right.
Yeah, this result that you showed today.
This result, yeah, I haven't used any CFT. Any details of the CFT. Just the fact that there is an OP between the stress tensor and scalar field.
Okay, thanks.
Okay, thank you.
Actually, Roji, just small questions. Because in the commutator, central charge dropped out, right?
The
difference when you computed the central charge.
This one. So this is basically,
there is central charge here, but when you computed the in the next slide, maybe in the
so basically the central charge can be thought of as some sort of normalization. There is no OP between this and
right
on the field.
No, even the unitarity of CFT is not clear if it's used at all, right? Your C could be negative and everything would go through.
Yeah. I haven't used anything. I don't know whether that will appear in non-trivial, but I could not see.
Okay, thank you.
The role of this term is to make sure that there is a conical singularity. Just at that point where I insert the wedge, the tip of the wedge.
But the G didn't depend on, of course, on the C.
Yeah, right.
Sorry, I think I got disconnected.
Sure.
Yeah, I was asking, I'm not sure if you heard this. So you do have a large N limit, right? Here. So
here I haven't for CFT. So this is the CFT I'm working with is just the CFT in the bulk and or in the Minkowski space-time where I haven't used any large N.
This is not ADS-CFT. This is Minkowski CFT in Minkowski, right? That's all.
Yeah, right.
No, I'm not. Yeah, I guess in the gravity, it will be some sort of semi-classical description.
Yeah.
Okay.
See, the main difficulty is if you go to complicated setup, computing the modular operator or the modular Hamilton is complicated. So for this case, we have wedge structure.
No, I mean the sub-region is Rindler and all that. That I agree. I'm simply saying that. So, for example, I have to be careful about whether these boost operators pertaining to region M or N, they are well defined or not, or whether I should use the extended or the full modular Hamiltonians, because the Hilbert space will become non-factorizable. But I think if you
right,
have
there are difficulties when you go to the bifurcation point, but that moment you can take the difference between the modular Hamilton on the right and left. So that is a different thing. If I consider the entire modular Hamiltonian, the full modular Hamiltonian involves the thing that is coming from the operator algebra and the commutant. So the total thing is always well defined.
Yeah, I mean the extended modular Hamiltonian becomes the left minus right.
Yeah, actually it's
modular Hamiltonians only when the left minus rights are well defined.
Yeah. So when I say,
separately.
when I say modular Hamilton, I just mean the full modular Hamiltonian.
Yeah.
That's why I just introduce this delta bar and
yeah. You are always working with deltas. Okay.
Yeah. So, but here I definitely use the fact that right in the right wedge and left wedge there is like things can be factorized in this simple case.
Yeah, that's why I was thinking whether you have some sort of large n limit or something in mind.
No, I haven't.
Okay.
Yeah.
Okay. Yeah. Any further questions?
I don't see anything in the chat, Devjyoti also.
Okay, so if not, let's thank Roji again, and we meet again at 7 p.m. for our last talk for today.
Okay, thank you.
Right, Roji, thanks a lot.
Thanks a lot.
Bye, Roji. Bye.
Okay, bye.
Bye. Yes, I'll stop recording.
Yes.